Hi everybody, welcome back. This is Michael Van Cleek's latest architecture video. As you might recall, we've been working on architectures of hope around COVID-19. It's such an interesting time we're in right now. And science is not really at the forefront right now. We have a lot of hysteria. We found hysteria travels very well over the internet, but science maybe not as well. So what I'm trying to do is offer some architectures to get people thinking about how we can use the technology that we have now, the cutting edge data streaming technologies, for example, to solve this global problem. There's some assumptions that go into this, of course, which is that people are working together, people aren't trying to sabotage our system, we don't have security built into here, for example. The assumption here is that people are well-intentioned and are sharing data. As we all know, that's not always the real-world situation, but we want to be a little bit Pollyanna-ish in my architecture, and I really believe that science gives us the opportunity to all work together. So I want to walk you through how we might be able to use Kafka and data queuing architectures, data streaming architectures, to create an architecture that enables the global community to work together to run tests on COVID data, analyze COVID data, and create solutions that will help the world move beyond this and will help us learn so that we don't repeat the same problem again. As we all know, viruses are evolving just like the rest of us. So with no further ado, I'm going to walk you through this flow that takes us from COVID testing through the population of the data store out to peer-reviewed data. All right, and I will be zooming in using my iPad, of course, as we've used in the past. I started here, as you know, I mentioned, showed a couple days ago on LinkedIn. I started with this hand-drawn architecture, and this basically stimulated my learning. I went from that to doing some research to make sure I really understood Apache Kafka, make sure I understood Apache Flink, and make sure I could walk you through something here that at least is a beginning. And some of this may not be technically correct, but it's a start. I wanted to give us a point of conversation to begin with. So we start, of course, with the people. And as we know, COVID's been spreading pretty well through churches, schools, conferences, places where people gather together. So we have all these people coming from various events. Over here on the left side, I don't really have a pointer I can use, but they're feeding into the COVID test sites, which are the red crosses. Each of these test sites would be gathering data about somebody who's a potential patient using an app and a web interface. And just talking about the data gathering, of course, one of the problems we have right now is the only people being tested are the sickest people, which is leading to massively inflated mortality rates, which are then being put into exponential calculations that freak out the whole world. So because we are starting with bad data with a small sample size, because of our limitations in our data infrastructure, we're in a panic state. But assuming that we had more test sites where more people, even people feeling perfectly healthy, could go in and get tested safely and confidentially, we would have that data come into some sort of app or web interface. And as you see in the top here, the test data would include results of your COVID tests, some basic demographic information, symptoms, timeline information about your households, etc. We have to be careful at all steps in this process to honor the anonymity of the person being tested, of the subject. One of the big fears that we're up against is, the stigma of being a positive test. There's people are going to be afraid to be tested if they know they could have this scarlet letter slapped on them. So we gather the test data in all these sites, and it's all of various quality, right? And then each of the submission sites, here's where we get into the technical part, would have an application that is connected into a Kafka queue. Amazon, for one, offers a managed Kafka service. Apache Kafka, is a platform for streaming data. It's designed to work with so many like Internet of Things, games, so many of the data-intensive applications that really define the internet today, really define the way we use computing. So we would create queues for each submission site or each submission cluster. Each of these submissions would obviously have their own their own application architecture, probably a simple 3-tier architecture. But each of them would link to a queue, which we are then in the central community data repository subscribing to. And that's this Apache Flink, Amazon Kinesis, purple square here that I'm moving into the center. So Kinesis, Amazon Kinesis is an implementation of Apache Flink. Flink is a data processing platform, a data processing technology that guarantees once only. Kafka doesn't guarantee that data is processed once only, but Flink does, and Flink is what is used for distributed, shared state, and stateful calculations. And we're trying to get Kafka, of course, its function is stateless. It's guaranteeing at least once processing on events. Flink guarantees once only, and it's good for when you bring that data in, doing things that need to be universally done on that data before it's shared. It's a basically an ETL, as we've always talked about: extract, transform. In the case of the Apache Flink here, what we would use Flink. So Flink is subscribing to these Kafka queues. We'd get the information. We would use Flink to make sure we have a shared timestamp. Each of these submission sites may have a different way of doing timing. We want to make sure that time is shared and we have a common time here. So Kinesis would make sure that each of the events has a time, that basic common time that would be used to populate downstream data sources, and would also be used to do any sort of securing and anonymizing of the data. If we need to take out particular location information, if we need to extract any connection from any sort of personal identifiable data, we would have jobs running in Flink to do that. So Flink has a series of jobs that are set up. They can be triggered by a queue off of the event. We see something, or an event off of the queue. So we see something coming into the Kafka queue. We see a test report off the Kafka queue. The Flink job would take that data, process it, and then Flink would write to several sinks as well. Flink is in itself built on top of Kafka, so the Flink architecture would be distributed. This data and the processing would be distributed, but Flink gives you a way to guarantee, again, that all the data is processed once and the state is shared, so we can bring it back together and then write it back out to queues for consumers to use. So in Apache Flink, we would again go ahead and do the anonymizing work, the timestamping. We know that each event would only be processed once, and then Flink would write to a number of outputs. One might be a data lake where we're taking all of the ready-to-consume test reports. So, in addition to the anonymizing and timestamping, we may have done some data cleansing, some Unicode conversion, some translating. All of those things may have happened in Flink. Once all that's happened, we can write those to a data lake that we might use for later, and then we can publish each of these test results to different Kafka queues, different topics. So again, using the Amazon managed Kafka service or our own Kafka implementation, we have these Kafka queues over here. Flink takes a test, publishes it to the appropriate queue. There might be different types of topics, maybe positive tests, maybe community tests. Maybe we have a topic that's just for tests, or we have household information. Maybe we have a topic that's just for tests in Europe. All of these different topics that can be, we set up filters on Flink to publish those, and then we have each of these queues out there, and these queues become publicly available. And the idea is that now each application that's being used to work with this data can subscribe to the appropriate queues and get updated information that's been massaged, that's been anonymized, so we don't have to worry about adding social stigma, and is clean and fresh, and it's timestamped, so scientists are enabled to look at particular time frames when they do their work. So those queues might be subscribed to by, as we see here, machine learning models, by reporting databases which connect to Tableau or something else like that. Whatever tools are being used to test hypotheses. So we have data scientists over here, immunologists, hobby data scientists, anybody who knows how to work with data, who are coming up with ideas about what's happening with COVID, how it's spreading. Is it spreading through households? Is it spreading in geographic isolation? Is it spreading at particular times? Where are those correlations? All these different questions. There's thousands of questions that we all have, but each of us only has the cognitive capacity to handle a couple of these questions. So by distributing the data, we empower data scientists, including a bunch of people who are being laid off and a bunch of people who are at home right now with a lot of time on their hands. We're empowering them to come up with hypotheses and test those against real-time data. So they would have set up everything, the data scientists would have to set up everything up to the queues. So you set up your reporting database, you set up your machine learning model, and your machine learning model is subscribing to the Kafka queue and getting that time-ordered, logged data. Kafka stores everything in a log and is distributed across log files. And while the whole Kafka implementation is a little bit beyond the scope of this, just understand that instead of it being a sequence of SQL joins, it's a log. It's like a log file. You can replay any part of that log through the queue to recreate a particular state, a particular period of time. So each of these models, each of the reporting databases would take its logged events that it's interested in that period of time, populate the information. The data scientists would execute their hypothesis against the machine learning model or against the reporting data. And when they see something that's valid, they now have some information that can be used to feed proposals or field tests or trials on particular hypotheses. Maybe one of the hypotheses could be a vaccine. Once we get that information tested. It can then go out into a peer review process. The WHO, if you've been following what they've been doing, they've been having to update their scientific processes to accommodate the rapid spread of COVID and the rapid spread of the science that's happening here. So we take the data scientists using this data coming out of Flink, this massage data through their queues, are creating more and more hypotheses and then are able to create proposals and tests and peer review all of this information before raising it up to a different level where it goes into the governance of the WHO and what's happening here to look for solutions. So I know this is a really short summary of a pretty powerful architecture. There's so much that's made possible by Flink, by Kafka, and by data streaming architectures. And the technology is surprisingly simple to use. It's primarily Java-based. Flink is mostly a Java API, but there's all sorts of different languages that go into it. And this is one particular application where we could be using Kafka and Flink right now to take all of this data that's coming from around the world about COVID, about testing, about incidences, about size of households, where people are traveling, and put all of this data into a format where data scientists can work with it safely and create a series of hypotheses and test them in their own test models before going to peer review. We need to create more knowledge and do more tests, but we also need to have a process that allows only the best tests and the most proven hypotheses with the data that back them to get up to the peer review and get up to the WHO. So I'm hopeful that we will come up with more and more ways to collaborate and share data. I think the epidemic has provided an unprecedented opportunity for collaboration, for updating our scientific processes, and for understanding how the world has changed, not only in the terms of how easy it is to pass a virus, but how easy it is for us to collaborate and share on testing information to make the world a better place. Thank you very much for joining me. Once again, Michael Van Cleek with my latest Architecture of Hope, an architecture for community work on COVID-19 test data. Thank you very much for following. Take care.